Hello friends, in this problem it is given that there is a conducting sphere of radius r containing two spherical cavities of radii a and b. Now these cavities have charges qa and qb placed at their centers. So with the help of this information we have to find the electric field and electric potential at a distance r in first part of the problem if this distance r is measured from point O, that is center of sphere, and in part B we have to find potential and field at distance r if this distance is measured from point B, that is the center of cavity 2, and this distance small r is less than b, that is in second case the point lies inside the cavity. And then finally we have to find the surface charge densities. So we'll talk about this second part later. Let us first solve part A of the problem. So this is our original diagram. Now we know that with the help of induction there will be induced charges. So I can write minus QA is the induced charges on inner surface of first cavity. Similarly for inner surface of second cavity it will be minus QB. And then the outermost surface of the conductor will have a net charge of QA plus QB. And with the help of this diagram we have to find the field and potential at this particular point. Let us call this point as point P1. So we can directly write the potential at point P1 to be equal to K QA plus QB divided by R, where QA and QA plus QB is the net charge on this outermost surface, and this result can be written with the help of electrostatic shielding. This simply means that this complete arrangement will have no effect on the outside point, right? So we can directly write with the help of electrostatic shielding that potential at point P1 will be due to the field generated by outermost charges, which will be equal to K QA plus QB by R. Similarly, field at this point will be equal to K QA plus QB divided by R square. Now what happens if this point lies inside the cavity 2? In second part of the problem it was asked if point lies inside cavity 2 at a distance r from it. So this is our point P2, which lies at a distance r from the center of second cavity where r is less than b, which means this point P2 actually lies inside the cavity. As you can see, this point lies inside the cavity. So for this particular point we can write that we can say that the potential at point P2 will be first the potential due to the charge present on the outermost surface of the main conductor, that is QA plus QB divided by R, plus potential created at this point due to charge minus QB, induced charge minus QB. The potential created due to induced charge minus QB will be KQB by B, plus finally the potential at this point created by charge present at the center, which is K QB by R. So this is the net potential at point P2. Field at point P2 will be due to the presence of this charge QB only, since we know that if a charge is present at the surface of a spherical surface, if the charge is present at the surface of a spherical geometry, we know that field due to that particular charge inside the spherical geometry is zero with the help of shell theorems. So we can write field at P2 will be due to the presence of charge QB only, that will be KQB by R square. And now it is again asked in the next part of the problem that we have to find the surface charge densities on the surface of radius r, a and b. So as we have already written the value of induced charges, we can simply write the surface charge densities on outermost surface to be equal to total charge divided by area. Similarly, surface charge density at the surface of cavity A will be charge divided by area of cavity A, and for B it will be again charge divided by area of cavity B. And in the last part of the problem, what is the force on QA and QB? So we are being asked the value of net force on QA and QB. With the help of electrostatic shielding we can say that the value of forces on QA and QB will be 0. This is the answer to part C of the problem. Thank you.